Welcome back to Sky Creative Channel. From the forges of the past to the factories of today, witness the incredible precision and power of modern manufacturing. This is how the world is built. Let me take you back to a craft that's been shaping civilization since the Iron Age. Here at Kovárna, a legacy forging company, they're keeping that tradition alive while pushing the boundaries of modern engineering. Today, we're witnessing the fascinating production of rolled rings, those circular steel bands that keep everything from wind turbines to jet engines running smoothly. NTHE process begins with raw steel billets heated in massive induction furnaces to around 200 degrees Fahrenheit. At this temperature, the steel glows bright orange and becomes malleable, much like the blacksmiths of old worked their metal, but on an industrial scale. The heated billet moves to the ring rolling mill, the heart of this operation. This remarkable machine uses two rollers, an idler roll on the outside and a pressure roll on the inside, working in tandem like a potter's wheel for steel. And as the billet is pierced and expanded, the rollers apply tremendous pressure, typically between 1,000 and 3,000 tons, gradually increasing the ring's diameter while reducing its cross-section. The beauty lies in the continuous grain flow this creates, making these rings incredibly strong without any welded seams. Mandrels and guide rolls keep everything perfectly circular as the ring grows from perhaps 2 feet to over 20 feet in diameter. Computer-controlled systems monitor temperature, pressure, and dimensions in real time, ensuring precision within thousandths of an inch. After rolling, each ring undergoes heat treatment to achieve the exact metallurgical properties required, followed by machining and rigorous quality testing. It's industrial poetry, really, watching centuries-old forging principles meet cutting-edge technology to create components that, quite literally, keep our modern world turning. There's something special about boat building that connects us to our maritime heritage. At Quintrex's facility, they're crafting the 7600HT Yellowfin. And folks, this isn't your grandfather's rowboat, though it carries that same dedication to craftsmanship he'd appreciate. Each hull demands over 80 hours of meticulous welding, a testament to the art that goes into modern aluminum boat construction. NTHE journey starts with marine-grade aluminum sheets, specifically 5083 and 5086 alloys, chosen for their exceptional corrosion resistance and strength-to-weight ratio. These aren't new materials. They've been the backbone of marine construction since World War II, when aluminum boats first proved their worth in military service. Using CNC plasma cutting tables, the sheets are precisely cut to patterns that have been refined over decades of Quintrex's boat building experience. Here's where human skill truly shines. Certified welders use MIG welding technology, feeding a continuous wire electrode through a shielding gas, typically pure argon for aluminum work. Each weld bead must be perfect because in marine environments, even the smallest defect can become a failure point. The hull pieces come together on specialized jigs that hold everything in perfect alignment. Critical because aluminum's thermal expansion during welding can warp panels if not properly controlled. NTHE transom receives reinforced welding, extra passes to handle the stress from outboard motors. The hull's bottom gets particular attention, with multiple welding passes creating watertight seams that'll withstand years of pounding through waves. Between major welding sessions, the aluminum must cool naturally. Rushing the process would create internal stresses that compromise strength. Quality control inspectors use dye penetrant testing, an old-school but reliable method where colored dye reveals any microscopic cracks or pinholes in the welds. Pressure testing follows, where the hull is sealed and pressurized to verify absolute watertight integrity. The riveted construction method, once standard in boat building, has given way to these superior, all-welded hulls that are stronger, lighter, and more durable. And every detail matters, from the precision welded rod holders to the reinforced anchor well. This 80-hour investment in welding isn't just about joining metal, it's about building confidence that when you're miles offshore, your boat will bring you home safely. That's craftsmanship that would make the old-time boat builders proud. Aluminum extrusion is one of those manufacturing processes that quietly revolutionized modern life. Here at Taiseer's plant, equipped with SMS Group Technology, they're transforming solid aluminum billets into everything from window frames to aerospace components. It's a process that traces back to the 1890s, but the precision and scale we're seeing today would astound those early pioneers. NTHE process begins with aluminum billets, cylindrical blocks typically 7 to 10 inches in diameter and up to 30 inches long. These billets start their journey in a gas-fired or induction heating furnace, brought to temperatures between 750 and 930 degrees Fahrenheit. Getting the temperature just right is crucial. Too cold and the aluminum won't flow properly, too hot and you risk damaging the metal's grain structure. NTHE heated billet transfers to the extrusion press, and this is where the magic happens. SMS Group's hydraulic presses generate forces up to 10,000 tons or more. Imagine the weight of a small cruise ship concentrated into a few square inches. A dummy block sits behind the billet, and as the massive ram advances, it forces the softened aluminum through a steel die, much like squeezing toothpaste through a tube, except this toothpaste is glowing hot metal, and the forces involved are astronomical. NTHE die itself is an engineering marvel, precision machine tool steel with openings that create the desired profile. Whether it's a complex hollow shape or a simple angle, the die determines the final form. As aluminum flows through at speeds up to 40 feet per minute, it emerges on the runout table, where powerful fans and water spray systems immediately begin cooling the profile. A DNA puller grips the leading edge and maintains consistent speed through the process. Stretchers follow, applying just enough tension to straighten the profile and relieve internal stresses. The continuous profile then moves to a precision saw that cuts it to specified lengths, often while it's still warm. Heat treatment comes next in aging ovens, where the profiles are held at specific temperatures to develop their final strength properties, a process called precipitation hardening. Surface finishing might include anodizing for corrosion resistance or powder coating for color. It's remarkable how SMS Group's automation systems coordinate every step, from billet loading through final packaging, maintaining tolerances measured in thousandths of an inch across profiles that might be 60 feet long. There's an old saying in metalworking that you can judge a company's quality by the finish on their steel. Here at Prakash Steel Products, they're producing bright steel bars, and the mirror-like finish on these products tells you everything about the precision and care that goes into every step of their manufacturing process. This is steel crafting that combines traditional metallurgical knowledge with thoroughly modern production methods. NTHE journey begins with hot-rolled steel bars arriving from the steel mill, still bearing the black scale and rough surface typical of hot working. These raw bars, usually in grades like 1018, 4140, or 8620, first enter a pickling line where they're submerged in hydrochloric or sulfuric acid baths. This chemical treatment dissolves the iron oxide scale formed during hot rolling, preparing the surface for the precision work ahead. It's similar to how craftsmen have been cleaning metal for centuries, just on an industrial scale. And after thorough rinsing and drying, the real transformation begins. The bars enter a cold drying process through tungsten carbide dies, and this is where the bright in bright steel comes from. As the steel is pulled through progressively smaller dies at room temperature, several things happen simultaneously. The diameter reduces precisely to specified dimensions, the surface becomes incredibly smooth and reflective, and the mechanical properties improve through work hardening. The drawing speeds can reach 300 feet per minute, with powerful draw benches applying forces up to 100 tons. What makes this process fascinating is the lubrication system. Special drawing compounds, often phosphate-based coatings combined with soap lubricants, reduce friction and prevent scoring of the steel surface. The dies themselves require regular maintenance and precise alignment. Any imperfection transfers directly to the product surface. And between drawing passes, the steel may require stress relief annealing in controlled atmosphere furnaces. These bright annealing furnaces use hydrogen or nitrogen atmospheres to prevent oxidation while heating the steel to around 200 degrees Fahrenheit. This restores ductility without sacrificing the smooth surface finish, a delicate balance that requires careful temperature control. NTHE straightening process uses multi-roll straighteners with up to 11 rollers that apply precise bending forces to remove any bow or twist. Precocious quality control doesn't miss a beat. Automated optical inspection systems scan every inch of surface. Ultrasonic testing checks internal soundness, and dimensional gauging ensures tolerances within 0.001 inches. NTHE final bars might undergo additional operations like centerless grinding for even tighter tolerances, or turning on CNC lathes for specific applications. Some grades receive special heat treatments, case hardening for wear resistance, or through hardening for maximum strength. Cut to length on precision saws, each bar is then carefully packaged to prevent surface damage during shipping. These bright steel bars become the precision shafts in machinery, the piston rods in hydraulic cylinders, the axles and equipment that needs to perform flawlessly. That mirror finish isn't just aesthetic, it represents dimensional accuracy and surface integrity that modern manufacturing demands. It's the kind of quality that built America's industrial reputation, now enhanced by the latest technology. Metal spinning is one of those ancient crafts that's been completely revolutionized by modern engineering. Repcon's hot spinning machines represent the cutting edge of this transformation, taking a process that craftsmen once performed entirely by hand and scaling it up to handle massive industrial components with remarkable precision. NTHE process starts with a metal blank, typically steel or high-temperature alloys, heated in an induction system to temperatures between 802, 200 degrees Fahrenheit. At this heat, the metal becomes plastic enough to flow, but retains sufficient strength to maintain its shape. The glowing blank is mounted on a mandrel, basically a form that defines the final internal shape of the part. Here's where Repcon's engineering brilliance shows. Multiple spinning rollers, sometimes 3 or more working in coordination, approach the rotating blank. These aren't simple rollers, they're hydraulically controlled tools capable of applying forces up to 50 tons each while maintaining precise position control. As the blank spins at speeds between 60 and 300 RPM, the rollers gradually push the hot metal against the mandrel, forming it into complex shapes that would be nearly impossible to create any other way. NTHE CNC control system orchestrates this mechanical ballet, coordinating roller position, pressure, and feed rates in real time. The process can create seamless cylinders, cones, hemispheres, or complex contoured shapes used in everything from rocket motor casings to pressure vessels. What makes hot spinning particularly valuable is its ability to work hardened material during forming, creating components with superior mechanical properties compared to casting or forging. NTHE finished components emerge with excellent surface finish and dimensional accuracy, often requiring minimal additional machining. It's industrial craftsmanship at its finest, combining the art of metalworking with the precision of computer control. Let me tell you about one of the most impressive steel production technologies to emerge in recent decades. Here at Electrotherm, they're using the HSMC process, horizontal single mold casting, to produce steel billets, and folks, this represents a fundamental rethinking of how we transform molten steel into solid forms, ready for further processing. It's innovation built on understanding metallurgy at its deepest level, and traditional steel casting has been around since the 1800s, with vertical continuous casting becoming the industry standard in the mid-20th century. But the HSMC process takes a different approach, one that offers unique advantages in product quality and production flexibility. Let's walk through exactly how this remarkable system works. NTHE process begins in the melt shop, where electric arc furnaces transform scrap steel and raw materials into molten steel at temperatures exceeding 900 degrees Fahrenheit. These aren't your grandfather's foundry furnaces. Modern EAFs use sophisticated electrode control systems and oxygen injection to achieve precise chemistry and temperature control. The molten steel's composition is carefully adjusted, with alloying elements added and unwanted impurities removed through slag formation. Oxygen sensors and spectrometers continuously monitor the melt, ensuring it meets exact specifications before tapping. Once the steel chemistry is perfect, the furnace tilts and pours its molten contents into a ladle, a massive refractory-lined vessel that can hold 50 to 150 tons of liquid steel. But here's what makes this special. The ladle isn't just a bucket. It's equipped with argon purging systems that bubble inert gas through the molten steel, removing dissolved gases and floating out non-metallic inclusions that would compromise the final product's quality. This refining process, called ladle metallurgy, can take 20 to 40 minutes, but makes all the difference in producing clean, high-quality steel NTHE ladle then moves to the casting position above the tundish, an intermediate vessel that serves as a buffer between the ladle and the casting machine. The tundish does more than just hold steel. Its design promotes flotation of remaining inclusions and helps maintain steady flow rates to the mold. Some tundishes incorporate filters or electromagnetic stirring to further refine the steel stream. Now we get to the heart of Electrotherm's HSMC innovation. Unlike vertical casting, where molten steel flows downward into water-cooled molds, the HSMC process casts horizontally. A water-cooled copper mold, oscillating back and forth to prevent sticking, receives the molten steel. The horizontal orientation offers several advantages. It eliminates the bulging and internal cracking, sometimes seen in vertical casting, allows for better control of solidification, and permits easy adjustment of billet size without major equipment changes. NA's molten steel enters the mold. Water flowing through channels in the copper walls rapidly cools the outer surface, forming a solid shell in just seconds. This shell, still only a fraction of an inch thick, must support the liquid steel core inside as it moves through the mold. The oscillation pattern is critical. Too fast, and you get surface defects. Too slow, and the shell sticks to the mold walls and tears. Modern systems use servo-controlled oscillators, running at precisely calculated frequencies and strokes. And beyond the mold, the billet enters the secondary cooling zone, where multiple rows of water spray nozzles continue the solidification process. This isn't just random spraying. Sophisticated control systems adjust water flow to each zone based on casting speed, steel grade, and billet size. The cooling pattern must be carefully managed to prevent thermal shock that could cause cracks. Some zones use mist cooling, others use direct water jets, all coordinated to ensure uniform temperature gradients. NTHE billet travels through the casting machine on support rolls, dozens of them arranged to support the solidifying steel without deforming it. These aren't passive rollers, they're driven and individually monitored for alignment and bearing temperature. Any misalignment could mark the billet surface or cause internal defects. In-temperature monitoring is constant throughout. Infrared parameters track the billet surface temperature at multiple points, feeding data to the control system. If temperatures drift outside acceptable ranges, the system automatically adjusts water flow or casting speed. Some installations even use electromagnetic stirring in the mold to refine grain structure and improve internal quality. In A's, the billet solidifies completely. Usually after traveling 30 to 60 feet through the machine, it reaches the cutoff station. Here, high-speed abrasive saws or torch cutting systems sever it into lengths typically ranging from 20 to 40 feet. Depending on customer requirements and downstream processing capabilities. The timing of this cutting is precise, based on casting speed and desired length. NTHE cut billets then move to a cooling bed where they gradually cool to ambient temperature. This controlled cooling is important. Rapid cooling could cause residual stresses or even cracking in some steel grades. Meanwhile, samples are taken for laboratory testing, checking everything from chemical composition to internal soundness using ultrasonic testing equipment. An SUR face inspection follows, with operators checking for any defects like cracks, seams, or surface irregularities. Billets that meet specifications move to storage, organized by heat number so full traceability is maintained. Each billet carries identifying marks linking it to specific production data, casting parameters, and test results. What makes the HSMC process particularly valuable is its flexibility and quality. The horizontal configuration allows easier maintenance access than vertical machines, reducing downtime. The solidification pattern produces billets with excellent internal soundness and surface quality, and the system can quickly change between different billet sizes, something that's costly and time-consuming with vertical casting. These billets become the starting material for countless products. They're reheated and rolled into rebar that reinforces concrete structures. They're forged into automotive components, drawn into wire, or machined into precision parts. The quality built into them during casting determines the quality of everything made downstream. Standing here watching this process, you're witnessing the culmination of centuries of metallurgical knowledge combined with cutting-edge automation and control technology. From the electric arc furnace's raw power to the precise choreography of the horizontal casting machine, every element works together to transform scrap metal into high-quality steel billets. It's the kind of advanced manufacturing that keeps industries running and economies growing, built on principles that steelmakers have refined for generations, but executed with technology that would seem like science fiction just a few decades ago. This is modern steelmaking at its finest, and companies like Electrotherm are showing the world how it's done.